All right, let's go ahead and get going on today's. So today, 4.1, second part, still dealing with inverses. Okay, but now we're actually going to write an equation for an inverse function, and then also talk about domain and range of the original function and how that corresponds to the inverse function. Okay, so the warm up here on the right, I say, are these one-to-one? So what does one-to-one mean again? What's it mean for a function to be one-to-one? Goes from one x value to exactly one y value. Okay, there's no duplicating. There's not two x's that go to the same y value. It's one x value goes to one y value. So on the right here in this box, 2x plus 5. Is that one-to-one? And specifically, there was an extra piece that we talked about. Yes, it is one-to-one. And how do we know, just based on the function, that it is one-to-one? Remember what I said about increasing or decreasing functions? If it is strictly increasing across the entire domain, negative infinity to positive infinity, it's going up the whole time, then yes, it's one-to-one. Or if it's going down the whole time, there's no peaks or valleys with it, okay? It's just strictly increasing or strictly decreasing. So we could say, yes, this one is one-to-one. What about the second one, x squared plus 2? No, why not? Okay, because that's decreasing and increasing. X squared we know is a parabola. We also had the horizontal line test. So if it fails the horizontal line test, it is not one-to-one. It can still be a function, but it's just not one-to-one. All right. What about a cubic? So x minus 3 cubed. Mason, why do you say yes? Yes. You're the only one who got in here now. Okay. So we know just x cubed looks like this. Okay. Even with a cubic, could I say that's strictly increasing? Is that one strictly increasing? As x gets bigger, does y get bigger? Yeah. Okay. So I think yesterday I might have made the comment on all linear. If it's linear, it will be one-to-one. Well, that was kind of stopping short. Strictly increasing, strictly decreasing is really how I want to specify that, because we can have some curvature to it. It's just we're not going to have a min or a max. Okay, that curvature going through the origin, I missed the origin a little bit, but it should be going through the origin. That curvature is still fine. It's an increasing function. As x gets bigger, y gets bigger. This could be negative x cubed, and it would be reflected over here. And this one, as x gets bigger, y gets smaller. So it's a decreasing function across the entire domain. So this one, yes, this one is also one-to-one. Okay, all right. So now day 2, let's actually write inverse equations. To write an inverse equation, first step, interchange the x and the y. So that one we had a second ago, it was f of x equals 2x plus 5, but if you wrote it as y equals 2x plus 5, your first step would be interchange those, and so you would say x equals 2y plus 5. So that's what I mean about interchange the x and the y. After you've interchanged the x and the y, then solve for y. Get it to be y equals, and not 6y equals, straight up y equals. So you might have to divide away the coefficient. And then the last step, you're going to replace your new function y equals with f inverse of x, or just f inverse. Your variable might not be x. to show with proper notation that this is the inverse function. So again, f inverse is f to the negative first. It's really not the negative first power, so it's not an exponent. It's simply the notation for it. Okay, so the last step, rewrite it with the correct inverse notation. Okay. All right, so let's actually find an inverse equation. So this was our warm-up. So f of x equals 2x plus 5. We confirmed that this is 1-to-1. So we've confirmed, yep, this one is 1-to-1. And if it is 1-to-1, then it has an inverse. Okay, so that 1-to-1 is important. So we spent all day yesterday talking about 1-to-1 functions. If it is 1-to-1, then it has an inverse. Okay, so really this is y equals 2x plus 5. If we want to find the inverse, this is where we switch the x and y. So now I would rewrite this as x equals 2y plus 5. So first step was switch x and y. Next, solve for y. So if I have x equals 2y plus 5, I could subtract 5 from both sides. And then I want to divide that coefficient of 2 away. So I end up with y equals x minus 5 divided by 2. Then from there, I'm going to replace the y with the correct inverse notation. So f inverse, and we'll even say f inverse of x, because x is our independent variable, would equal x minus 5 divided by 2. We could also do a quick heart surgery on this, and this is 1/2 x minus 5/2. So that would be the inverse function of 2x plus 5. Okay, this was also the problem from the warm-up, and we confirmed that this is not 1-to-1. So it does not have an inverse, but let's prove that this does not have an inverse. Okay, so y equals x squared plus 2. We could switch our x and y, so let's say x equals y squared plus 2. So then x minus 2 would equal y squared. To undo the squaring, we would take the square roots of both sides. So what do we have to remember if we are undoing a squaring as we continue to solve? What's special about that? Plus minus. So this is plus minus square root of x minus 2 equals y. Okay, if we are undoing a squaring, it doesn't matter what the variable is. If we're undoing a squaring, we have to include that plus minus. Okay, so what this is saying is that, well, I'm not going to write it as an inverse because it's not a true inverse. It's saying that y will be a positive x minus 2, but also y will be a negative square root of x minus 2. Okay, Maddie? I'm fine with you writing the plus minus, and then I'm elaborating on the significance of that plus minus.
Yeah.
Okay. So reason why this does not have an inverse is because we end up with two y values essentially. Okay. And again, we can't have two y values. So this is proving that it is not one-to-one. Okay. And then the last one from our warm-up, we already said, yes, this is one-to-one. So because it's one-to-one, we can find the inverse. So let's do this one for practice. Y equals x minus 2 cubed. I do my switch. I'll have x equals y minus 2 cubed. To solve for y, I'm going to do the cube root of each side. So that leaves me with the cube root of x equals y minus 2. There's no plus or minus or anything going on. We didn't undo any squaring. Okay. So the cube root of x equals y minus 2. So therefore, the cube root of x plus 2 would equal y. Writing it with inverse notation, we'd write f inverse of x equals the cube root of x plus 2. That's the equation for the inverse function. Okay, let's do another one. So say we have the function 2x plus 3 all over x minus 4. And this function is valid for any value of x not equal to 4. So I put that stipulation in there because if you put 4 in there, it's undefined. We want to find the inverse of this. So I'm going to immediately jump ahead because now we're comfortable. All we're going to do for our first step is switch x and y. Now we have to solve for y. So 2y plus 3, y minus 4. We have two y's going on in here, so this one's going to be a little more work. Okay. If I were to multiply both sides by y minus 4, that would go to that useful form of 1. So all I have on this side is 2y plus 3. But then I had to do the same thing over here, and I'm going to have x times y minus 4. So I'm multiplying both sides by y minus 4 to eliminate the fraction on the right. Remember, we're trying to solve for y. So this is going to take some manipulation to be able to get y by itself. All right, well, first thing, I'm going to distribute this in. So I'll have xy minus 4x equals 2y plus 3. I'm going to get all my y's on one side. So I'm ultimately trying to end up with y equals something. So this would be xy minus 2y would equal a positive 4x plus 3. Okay, I'm trying to get y by itself. I have x times y, but also a negative 2 times y. I can actually factor out that common multiple of y. So I could say y times x minus 2 is the same thing as x times y minus 2y. So this is an easy step to overlook when you are trying to solve for a variable and it occurs more than once. There's going to be some factoring that you're going to have to do. And it's factoring in terms of just factoring it out a greatest common factor. It's not making a cross or doing any of that stuff. So you have more than one variable going on, no big deal. Get them on the same side, factor it as a greatest common factor. So then y would be 4x plus 3 all over x minus 2. And we've solved for the one y variable. Writing it in proper inverse notation, 4x plus 3 all over x minus 2, with the stipulation that x cannot be what? 2. Okay, so for this one, we write the inverse function, but we also have to add in there that x cannot be 2, because it's not valid if x is 2. So x cannot be 4 in the original function, it cannot be 2 in the inverse function. Okay, let's do another one, and on this one we're going to identify domain and range of each. Okay, so this one, if we wanted to solve, I'm immediately jump to say square root of y plus 5, make my switch right off the bat. To undo the square root on the right, I'll square both sides. So I have x squared equals just a y plus 5. So then x squared minus 5 is equal to y. Or I could write it as f inverse of x is x squared minus 5. All right, so this one's pretty straightforward. But now let's talk domain and range. If we're looking at the original function, f of x is square root of x plus 5. What is the domain of this function? What possible x inputs can I put in to this original function here that I'm working with? Can I put in 0? Yep. Can I put in -5? Yes. Can put in -5 because square root of 0, square root of 0 is 0. That works. Okay. But they also tell me that x has to be greater than or equal to -5. So if we were to write this out in interval notation, I would say -5 inclusive all the way up to infinity. Now, what about the range of a radical? Okay, we already talked, we can get 0. If we put in -5, we get square root of 0, which is 0. Can I get a negative number? Nope. So the smallest it's going to be is 0, but I can include 0 all the way to infinity. And we've graphed radical functions. We know it's that looks something like this. This x plus 5 means it's going to be shifted over 5 units. So it's going to look something like that. Now, if I want to identify domain and range of my inverse function, okay, so domain, range, let's think of this graphically first. x squared minus 5. What shape is that going to take? Parabola. What's the minus 5 telling us? Shifted down 5 units. So it's going to look something like that. So x squared minus 5, it's going to look something like that. Okay, let's first look at the range. So the outputs of this one. Will I ever get for a y value -6? Nope. Will I ever get -5? Yeah. And then -4, 0, all the way up from there, because it cuts off here. The smallest it's going to be is this line y equals -5. So my range is actually -5 all the way to infinity, but I'm going to include that -5. Now this is where it gets kind of, well, first off, let's see if we recognize anything. Look at the domain and range that we have filled out so far. We can see that the domain of our original function is the range of our inverse function. Okay, don't think about those switching or anything, not like coordinate points that are switching. The domain of the original is the range of the other one. And then, oops, the range of the original becomes the domain of the other. So those switch, domain and range switch. Would you say, well, that doesn't make sense, Mr. Army, because, yeah, x squared minus 5 is a parabola. I could have anything on there, any value that'll work. Well, it's still playing off of the original function, where this one, you could almost think if this one continued on, it would look like a sideways parabola, and it's shifted. And so really, these points do not exist. And so on here, they're not going to exist either. Okay, but the biggest thing you have to remember is they switch. The domain of the original becomes the range of the inverse. The range of the original becomes the domain of the inverse. Okay, they're the exact same, they just switch. Okay, all right. So just a summary about everything we've talked about with inverses here. If f is 1-to-1, passes the horizontal line test, it's strictly increasing or strictly decreasing. For every unique x, we get exactly 1y. It's 1-to-1, the inverse exists. The domain of f is the range of f inverse. The range of f is the domain of f inverse. Okay, so we said those switch. If the point AB lies on f, then BA lies on f inverse. So we talked about that yesterday when we had a relation. We had all those coordinate points laid out. We could just switch the x and the y coordinates, and that would give us our inverse coordinates. Okay, because again, it's a reflection across the line. Oops, across the line, y equals x. It's going to reflect over that line. So that's why our coordinates switch. Oh, right there, step number 4. The graphs of f and f inverse are reflections of each other across the line y equals x. And this ties in on the last example. When we started out with, when we said y equals square root of x plus 5, well, if I were to reflect across this line y equals x, then my reflection would look something like that. And this might be a better visual of why when we did x squared minus 5, the left side really was not valid for a domain. All right, so this idea of this reflection across, because our original function y did not have any points below the x-axis, when we reflect it over, it's going to look like that. It's going to stop at the y-axis and then continue on. So this was y inverse x squared minus 5. Okay, and to find the equation, so if you determine that it's 1-to-1, to find the equation of the inverse, you're simply going to interchange the x and the y, or whatever variables you're working with. It could be a equals 2b plus 7. Well, you would get it out to be b equals then. So you'd move stuff around. Okay, and after you interchange and solve for the y, that is your f inverse. Okay, I'll leave this up here. Next slide's the same. Get started on the assignment. 4.1 day 2 is in Math Excel, due before the start of class tomorrow.